Hello everybody. In this video we are going to be looking at the solutions to the college prep electromagnetic induction practice problems 2. Let's take a look at problem number 1. Jacob is pedaling his bike down the street perpendicular to the Earth's magnetic field of 5.5 times 10 to the minus fifth Tesla. What is the flux through the metal rim of his bicycle wheel if the wheel has an area of 1.13 square meters? In this problem, we are given the strength of the Earth's magnetic field of 5.5 times 10 to the minus fifth Tesla. We are given the area of the wheel, 1.13 square meters, and we are being asked to find the magnetic flux, or phi. I know that the magnetic flux is equal to the magnetic field times the area. So I just have to take my value for the magnetic field, multiply it by the area, and that is going to give me a magnetic flux of 6.2 times 10 to the minus fifth Weber. And remember, this is our symbol or our unit for magnetic flux, the Weber. Problem 2. John is pedaling his bike down the street perpendicular to the Earth's magnetic field of 5.5 times 10 to the minus fifth Tesla. What is the induced voltage in one metal rim of the bicycle if the wheel has an area of 1.13 square meters and it takes 2.0 seconds to make a 90-degree turn into a northbound street? A couple of things I want to point out before we look at the math for this problem. We know that after he takes his 90-degree turn, he's going on a northbound street. So we can presume that before that, he was traveling either east or west. That's important because if he's going perpendicular, and this is a key word right here, he's traveling perpendicular to the Earth's magnetic field, he's going to have the maximum number of magnetic field lines passing through the rim of his bicycle, which means that his magnetic flux is going to be at its maximum value. Once he makes this 90-degree turn onto a northbound street, he is then going to be parallel, or the wheels of the bicycle more specifically are going to be parallel with the Earth's magnetic field, and that's going to essentially bring the magnetic flux down to zero. So we're going from a maximum flux to no flux. Let's take a look and see what we are given in the problem. We are given the magnitude of the magnetic field of the Earth, as we were in the previous problem, 5.5 times 10 to the minus fifth Tesla. We are again given the area of the bicycle, which is the same as in the previous problem, 1.13 square meters. And we're given the time it takes for him to make the turn onto the northbound street of 2.0 seconds. And we're going to treat the bicycle rim as if there is only one turn or one coil in the loop, and really it's one big metal piece. So that is a good assumption. And we are looking for the induced voltage or the induced EMF, which we represent by our Greek letter epsilon. So to find the induced EMF, we are going to have to use Faraday's law. And I know that the induced EMF is going to equal the number of turns times the magnitude of the magnetic field times the area divided by the time. I plug my known values into that equation, and I'm going to get an induced EMF of 3.1 times 10 to the minus fifth volts. Problem 3. While out for a walk with his mother, Lance notices a large cylindrical gray box high atop a telephone pole. His mother explains that it is a transformer. This transformer takes 6.0 times 10 to the third volts from the power company and steps it down to 240 volts supplied to each of the houses on the street, with the use of a secondary coil containing 100 turns. How many turns are there in the primary coil? So I know my primary voltage in this problem is 6,000 or 6.0 times 10 to the third volts. I know that my secondary voltage, or the voltage coming out of the transformer, is 240 volts. The number of turns on the secondary coil of the transformer is 100 turns, and they are asking us to find the number of turns on the primary coil. So I know that I'm going to use my transformer formula, and my transformer formula tells me that the ratio of the secondary voltage to the primary voltage is equal to the ratio of the number of turns on the secondary coil to the number of turns on the primary coil. And we want to solve this for the number of turns on the primary coil. So again, the best way to solve these is to cross multiply. So I'm going to cross multiply. You guys remember doing proportions in your math classes. This is the same thing. So I'm going to cross multiply, and then to solve for the number of turns on the primary coil, I have to divide both sides by the voltage of the secondary coil. When I do that, I'm going to have NP equals VP times NS divided by VS. I plug my known values into that equation, and I'm going to get a value of 2,500 turns on the primary coil. One thing I do want to point out is that remember that the voltage and the number of turns are directly proportional to one another. So if you look at the voltage on the primary compared to the voltage on the secondary, you notice that there are the voltage of the primary is 25 times greater than the voltage of the secondary, and there are 25 many turns on the primary coil as there are on the secondary coil. So that is proportional. Problem 4. A medical process called magnetic resonance imaging, or MRIs as we know them, replaced X-rays in some instances where pictures are required to study soft internal organs. Nancy is undergoing an MRI procedure and is placed inside a chamber housing the coil of a large electromagnet that has a radius of 25 centimeters. A flux of 0.290 Weber passes through the coil. What is the strength of the magnetic field inside the coil? We are given the radius of the coil, 25 centimeters. We do have to convert that to meters, so that's 0.250 meters. We are given the strength of the magnetic flux passing through the coil, which is 0.290 Weber. And we are being asked to find the strength of the magnetic field. I know I'm going to need to know the area of the coil of wire. So to find the area, I know I have to take the radius, square it, and multiply it by pi. When I plug my radius of 0.250 meters into the formula, I'm going to have an area of 0.196 square meters. Now I know the magnetic flux is equal to the magnetic field times the area. So if I want to solve this for the magnetic field, I'm going to have B equals phi divided by A. I plug my known values into that equation, and I'm going to have a magnetic field of 1.45 Tesla. Problem 5. Audrey disassembles the control box of her electric train and finds a small transformer inside. Its primary coil is made up of 600 turns, and the secondary coil is made up of 60 turns. A. If the household voltage supplied to the train is 120 volts, what voltage is required to make the train run? And B. Is this a step up or a step down transformer? First of all, what's up with Audrey? Why is she taking this thing apart? I'm sure her parents paid good money for this electric train, and she's just taking the darn thing apart. I know if I was Audrey's parent, I wouldn't be too happy with the kid. And it'd be the last time I ever bought her an electric train. I could tell you that. All right, let's take a look at the problem. We know that the number of turns on the primary coil is 600. The number of turns on the secondary coil is 60. My input voltage into the transformer is 120 volts. And we're being asked to find the secondary voltage, or the voltage coming out of the transformer. Again, I use my transformer formula, and I know that the ratio between the secondary voltage and the primary voltage is equal to the ratio between the number of turns on the secondary coil to the number of turns on the primary coil. As before, we will cross multiply, solving for the secondary voltage. I'm going to want to divide both sides by the primary number of turns, and I'm going to get VS equals VP times NS divided by NP. I plug my known values into that equation, and I'm going to have 12 volts on my primary, on my secondary voltage. So I'm going to have 12 volts coming out of the transformer. And because the secondary voltage is less than the primary voltage, I know that this is going to be a step down transformer. We're stepping the voltage down or decreasing it. Another thing to point out is note that there are 10 times the number of turns on the primary coil as there are on the secondary coil, and my primary voltage is 10 times my secondary voltage, so they are proportional. That's always a good way to double check your work. Problem 6. A hydroelectric plant in Niagara Falls sends 3.00 times 10 to the third volts to the transformer in a substation that steps it up to 1.20 times 10 to the fifth volts for transmissions to homes in New York City. If the primary coil contains 2.00 times 10 to the third turns, how many turns are there in the secondary coil of the step-up transformer? So we are stepping the voltage up from 3,000 volts to 120,000 volts. Let's take a look and see what we are given. The primary voltage is 3,000 or 3.00 times 10 to the third volts. The secondary voltage, or the voltage coming out of the transformer, is 1.20 times 10 to the fifth volts, or 120,000 volts. The number of turns on the primary coil is 2.00 times 10 to the third turns, or 2,000 turns, and we're looking for the number of turns on the secondary coil of the transformer. Once again, we use our transformer formula. When we cross multiply and solve for NS, we are going to get NS equals VS times NP divided by VP. We plug our known values into that equation, and we are going to get the number of turns on the secondary coil is going to be 8.0 times 10 to the fourth turns, or 80,000 turns. Problem 7. A 2.5 watt wire is curled into an elliptical loop with an area of 1.2 square meters and is placed horizontally on a table where it is embedded in a 30.0 millitesla magnetic field that points upward. The ends of the ellipse are then pulled, stretching it out and reducing the area to 0.10 square meters. As the ellipse narrows, a current of 3.6 milliamps is generated in the wire. How long does it take to change the chain to that? I'm going to try that again. How long does it take to change the ellipse's shape? Lots to unpack in this problem. Let's just see what we're given. We know that there is one loop in the wire. It is a singular loop. We use the singular tense, so we can assume that there is one loop. I know that the power in the wire is 2.5 watts. My initial area of the ellipse is 1.2 square meters. The final area of the ellipse is 0.10 square meters. The strength of the magnetic field is 30.0 millitesla. So I have to convert that to Tesla. So that's 30.0 times 10 to the minus third Tesla. The current that is generated in the wire is 3.6 milliamps. Again, we have to convert that to amps, so that's 3.6 times 10 to the minus third amps. And we're trying to find the time. We know we're going to need to use Faraday's law of electromagnetic induction. And to use that to solve for time, I know I'm going to need to know the induced EMF in the coil. I'm not given that, but I am given the power and the current. And I know that the power is equal to the current times the voltage. So I can say that the power is equal to the current times the induced EMF in the wire. And yes, I know that says pi. Deal with it. Solving that for induced EMF, I know that epsilon equals P divided by I. I plug my known values into that equation, and I'm going to get an induced EMF of 694 volts. Now I can go to Faraday's law of electromagnetic induction. And I know that Faraday's law of electromagnetic induction is N equals B times the change in the area divided by T. Solving that for T, I know I'm going to have T is going to equal N times B times delta A divided by epsilon. Note real quick, we are ignoring the minus sign right now, and I'll talk about that when I get to the end. When I plug my known values into the equation and I solve for t, I'm going to have a time of 4.8 times 10 to the negative fifth seconds. Now note I've ignored this negative sign as I've moved through there. Remember that negative sign, as we've described before, just simply means that as the loop of wire rotates and it goes from top to bottom and it rotates 180 degrees, that the induced EMF is going to be reversed. That's all that negative sign means. So we can kind of ignore it just to get the magnitude or the value for the time.